we're presenting our work on parallelizing the problem of string art. String art is a technique for the creation of visual artwork where images emerge from a set of strings that are spanned between pins. In this system flow diagram, we see that for the string art problem, the input is the image, the width of output, and the number of pins. And the output is the string art instruction and visualization. Given inputs, some image processing and pin location computations occur first, and then the majority of the workload is in finding string path. This is the section that we are parallelizing. Here's the approach we took. We chose the algorithm that produced the output better resembles the input than a more common solver. It is a greedy approach that has more computation. Inside the pink box, there are the add stage and the removal stage. The greedy approach starts with the add stage, finding a string that minimizes the norm, adding it, and keep doing it until no more string addition can improve the norm. Then it enters the removal stage. It looks at all the previously added lines and compute the norm for if the line is removed. If the new norm is better than the current norm, it removes the line. This is done to every string until no more removal can improve the norm. Then it enters the addition stage again. It alternates between the two stages until no addition or removal can further minimize the norm. As for implementation detail, our images and constructed images are stored in char array concatenated by rows. The lines found are stored in arrays for easy parallel access. We anticipated the challenge of implementing a sequential version that contains all the data structures ready to be parallelized. As we improved our CUDA version, we had to change a few things to our sequential version. We changed a Q data structure to an array to avoid data dependency. We changed the assumption of a pick yarn to avoid giant memory footprint and to produce output that better resembles the input image when the image size is small. We exploit line-level parallelism in our CUDA implementation. When finding a line to add, we parallelize over all pin pairs. When finding a line to remove, we parallelize over pin pairs added.
Here are some example inputs and outputs for our benchmarks. The first row are photo inputs. The second row are outputs with diameter 512 and 128 pins. The third row are outputs with diameter 512 with 256 pins. We did our benchmarks on GHz 47 to 86 machines containing the NVIDIA GeForce RTX 2080B GPUs. The baseline algorithm is designed for a single thread CPU run on the same machines. We measured clock times in seconds for computing the pin pairs needed to fabricate the string art and compute the speedups. Let's first look at the graph on the right. When a problem size is relatively large with diameter 512 and 128 pins, we see 72x to 221x speedups. Here we're proud to say that parallelizing string art on GPU was a good choice due to the large number of subproblems without data dependencies. For smaller problem size in the middle with diameter 512 and 64 pins, we see 25 to 42x speedups. We can also see that the execution time varies quite a lot using the sequential version. The variation is much smaller using CUDA. We speculate that this is because of the relatively small number of while loop iterations. And for an even smaller problem on the left with diameter of 128 and 32 pins, we said there's not much variance among images. And this is caused by when the image size and number of pins are small, different input images will yield the same output, which causes a similar execution time. However, even with small problems like this, with CUDA memcopy overheads, we still see a bit speed up. Looking at these three graphs together, we see the performance of our CUDA implementation heavily depends on the problem size. The larger the problem is, the better the speed up. Recall that our CUDA parallelism only has line-level parallelism, but not pixel-level parallelism. Our CUDA implementation's execution time is still heavily dependent on both image diameter and pin numbers. Because line length is affected by image diameter, and so is the number of iterations of the sequential while loop. As either parameter increases linearly, complexity-wise, our problem increases quadratically. To conclude the results section, our parallelism performance is heavily problem size dependent. The larger the problem size is, the better the speedup is, and the sequential while loop limits the speedup. Finally, these are references we use for this project. On the top right corner was one of the earliest output images we produced based on the algorithm proposed by the paper. Could you guess who this is?